Welcome back. Here is the last example on optimization. Let's say a rectangular box is to have a square base and a lid and a volume of 12 cubic feet. The cost per square foot of material for the base is 50 cents, and for the sides, for the four sides, it's 20 cents, and for the lid, it's 10 cents. And we want to find the dimensions of the box that will minimize the total cost of materials to build the box. Okay, so as usual, you should be reading this statement a couple of times to make sure that you understand what is given and what is being asked. So here we are given that we have to build a box with 12 cubic feet of volume. That's requirement 1. The requirement 2 is that the base of the box and the lid, I guess, should be square. And then we need to minimize the cost of building such a box, where the prices for building the sides are given. So we have a box where the base is a square, so the length and width of the base are the same. So let's say x is the length of each side of the base, and so the top has the same dimensions as the base, and let's say h is the height of the box. Okay, so let's look at the cost of building the base. The cost of building the base would be, well, the base has an area of x squared. So x squared is the area of the base, and for each square foot, we have to spend 50 cents so to build the base. So we have to multiply 50 cents with x squared to get the total cost of building the base. For the top or the lid, it's 10 cents. So we have to multiply 0.10 with x squared, which is the area of the top, to find the cost of building the top. And okay, so what's the area of the four sides here? Well, the area, well, the dimension of each of the four sides is the dimensions of each of the four sides are h and x. So the area of each side here would be h times x. So for the four sides, it'll be a total of 4 times x times h. So that's the area of the sides, and we have to multiply that by 0.2 to find the cost of building the sides. So so the volume is x squared times h. So volume is the area of the base times height, and that's equal to 12. That's the requirement. And from this, we can solve for h and get that h is 12 divided by x squared, which can also be written as 12 times x to the negative 2. And so this is our constraint, that the volume has to be 12. Now, the base will cost, like I said, 0.5 times x squared. The lid will cost 0.1 times x squared, and the four sides will cost 0.2 times 4xh. So the total cost of building a box with sides xxh is given by this, and so we can rewrite that as 0.6x squared plus 0.8 xh, and using the constraint here, we can replace h by 12x to the negative 2. So we need to minimize the total cost function c of x, which is 0.6x squared plus 0.8x, and h is replaced by 12x to the negative 2. Simplify that down to 0.6x squared plus 9.6x to the negative 1. And we can require that x is positive here because x couldn't be negative because we are talking about the length of a box. So now we have to minimize the cost function on the interval from 0 to infinity. The derivative of this function, is by the way, we know that x could be any positive number here because so here you can see that I can pick x to be whatever positive value I want, and then I have to pick h as the ratio of 12 and x squared to make sure that the volume stays at 12. So if I pick x too big, then I have to pick h too small, and if I pick h too big, then I have to pick x too small to make sure that the volume remains 12. Okay, so the derivative would be 1.2 times x minus 9.6 times x to the negative 2, and then we can write x to the negative 2 as 1 over x squared, and then that we can write it as 1.2 x cubed minus 9.6 divided by x squared. Okay, so the derivative is 0 when the numerator is 0, and the numerator is 0 would mean that x cubed is 9.6 divided by 1.2. Okay, I'm sorry. I am factoring out 1.8. If I factor out 1.8, then I'm getting x cubed minus 8 because 9.6 divided by 1.2 is 8. So now I can see that the derivative would be 0 if x cubed is 8. And x cubed is 8 when x is exactly 2. So that's the only critical point that we get. And let's apply the second derivative test, the second derivative of c prime. So let's use this one. So what's the second derivative? Well, it'll be 1.2 plus 9.6 times 2, which would be 19.2 x to the negative 3. And the second derivative evaluated at 2 is clearly positive, which means that we have the cost function is concave up at the critical point 2, so it has a local minimum at 2, and being the only critical point, that's got to be the absolute minimum. So the absolute minimum of the cost function occurs when x is 2, and so the minimal cost happens when x is 2, and if x is 2, then we know that h is 12 divided by x squared, so it's 12 divided by 2 squared, which is 3. So if we pick x to be 2 and h to be 3, then the volume would be 12, but we can minimize the cost. Now obviously we could build other boxes, like we can pick x to be 1. In that case h would be 12, or we can pick x to be, let's say, 4, and then h would be 12 over 4 squared, or 12 over 16. And for those choices, you can figure out the cost, and you'll see the cost for any other choice of the dimensions would give us a higher cost. Okay, so this is it. That's the end of this problem, and I hope that you feel comfortable with optimization problems. And if you have any more questions, please feel free to ask when we meet in the class.